Hi. So we have been discussing the wave function. Okay. And I think during most of the course we will be discussing the wave function. As we discussed earlier, the wave function is the coordinate representation, all right, or the representation of the state vector or the vectors, the abstract vector in Hilbert space. They can be represented in the basis, okay, formed by the eigenstates of the position operator. Right, so we call that the coordinate basis. We could also use the momentum basis. Then we have the momentum space wave function, and we said these are related by a Fourier transform. Okay, these things we have discussed. Okay, let's now look into the probability interpretation, right, and some of the things related to that. So this psi of x comma t, okay, it's generally a complex quantity. All right, so the quantity that appears, or the quantity that you can find by solving the Schrodinger equation for a given situation, that's a complex quantity, all right, or the wave function corresponds to. It's actually a number, a complex number. This actually gives a complex number associated with each point in space. Okay, so you give as the input of this function, you give a space, all right, a point in space, a three-dimensional space. This function will give you a complex number, all right. That's the wave function. Okay, so associated with every point in space, you have a complex number. So assigning this complex number is done by the wave function. Okay. Now this is usually we are discussing for a single particle case. For two particle case, for example, we have additional complication with entanglement, etc. We will be coming to that later on. All right. So for now we are discussing it as a single particle, or the wave function representing a single particle. Okay. So since this is complex quantity, it's not very good to assign direct physical significance to this number. All right. So for example, okay, so sometimes people call this wave function as some real wave in space. All right, that's a misunderstanding. So as we discussed during the wave particle duality, so there's no reason to think of this as some real wave in space. All right, because if you take a two particle system, we still have numbers, but these waves, all right, for a single particle, of course, the single particle, this wave, all right, or this field, this probability amplitude field, if you like, or this wave, it looks like a wave in three-dimensional space. Okay? But once you have two particles, you get a complex number for each configuration of this two particle system, or each configuration of this two particle system, which means that we will be dealing with complex numbers associated to every point in a configuration space. Okay, that's not a real space. So if you have two particles, if you need, let's say, three numbers to describe one particle, the position of one particle for two particles, right? So the two particle space is actually six-dimensional. The configuration space is six-dimensional. Okay. Now for a two particle system, the wave function, the quantum mechanical wave function, gives you a number for every point in this six-dimensional space, all right, for every point in this six-dimensional space. So for this reason, it's not good to assign any direct physical significance for this quantity wave function, all right, but it has an interpretation. If you take the modulus square of this wave function, you get a real number, all right. If you take a complex number and take the modulus square, you get a real number. Okay. This real number is physically significant, and it is defined as the position probability density, or rather interpreted as the position probability density. Okay. This means the probability of finding the particle per unit length at time t. Right. So if you remember, we have discussed this thing. All right. If you have a discrete basis, we can write the arbitrary vector in Hilbert space as, or any arbitrary vector in that Hilbert space as summation over I ci phi I. Okay, this phi I could be the eigenvectors. Okay, we have discussed this eigenvectors, okay, of some operator, some Hermitian operator, of course. Okay, some Hermitian operator. Let's say H cap. Okay, it could be the Hamiltonian operator, for example. All right. So if these are the eigenvectors of the Hamiltonian operator, then we are expanding the given state vector in terms of the eigenvectors of the Hamiltonian. Okay, and then in this case, the interpretation for this expansion coefficients is that modulus of Ci square, okay, modulus of Ci square is the probability is the probability for measuring a particular value for energy corresponding to the particular eigenstate phi I. Alright, so if phi I is an eigenstate, let's say phi I is an eigenstate of the Hamiltonian with eigenvalue Ei. Alright, if phi I is an eigenvector of the Hamiltonian with eigenvalue Ei. Okay, then modulus of Ci square gives you the probability, or for modulus of Ci square, you can find the probability to measure an energy value Ei. Alright, so the question asked is, right, what's the probability that you will measure? If you want to measure the energy of the system, what's the probability of measuring an energy Ei? Okay, it could be E1, E2, E3, etc. Okay, and quantum mechanics tells us that this probability can be found by obtaining modulus of Ci square. Okay, of course, you have to normalize this coefficients, because if these are to be interpreted as probabilities, the total probability has to be 1. Right, so summation over, we need to demand that summation over I modulus of Ci square is equal to 1. Okay, this is for the discrete case. This is for the discrete case. Okay, fine. Now, what happens? Okay, if instead of a discrete basis, we use a continuous basis. For example, the eigenvectors of the position operator. Okay, in that case, we can write the same vector as integral psi of x dx. We have seen this. Alright, it's exactly like this, except that for every point now you have got an expansion coefficient. Alright, if you call Ci as the expansion coefficient, for every point you have this complex number. Okay, so you cannot simply add them, it's continuous. So instead of the summation here, you have an integration. Alright, so here modulus of Ci square is the probability, here modulus of psi of x square is the probability density. Okay, it cannot be the probability because this is continuous and we have an infinite possible positions. All right, if we have got an infinite set of possible positions in space. All right, there are infinite number of points in space. Okay, so since there are infinite number of points, all right, since there are infinite number of points in space, if you ask the following question, what's the probability of finding the particle anywhere, all right, at any given point? Since there are infinite number of points, this probability will be 0. Right? So since there are infinite number of points in space, if you ask the following question, what's the probability of finding the particle at one particular point in space? This is 0 because there are infinite number of points, all right? But a legitimate question that we can ask is, what's the probability of finding the particle in a certain interval dx, all right? What's the probability of finding the particle in a certain interval dx, okay? And that is given by psi star psi, right? Or modulus of psi of x square. So it's the probability of finding the particle between x to x plus dx, okay? X to x plus dx, so in between the points x and x plus dx. All right, so for continuous wave function, we need to calculate the probabilities in this fashion. All right. So now modulus of psi of x comma t square dx is, now this is the probability of finding the particle or the electron in the interval dx. All right, so for this reason, we call this part as the probability density. We call this as the probability density. Okay, so in 3 dimension, you can call this as the probability per unit volume. Okay, so if you need to find the probability, you need to multiply it with a small volume element. Right, so the question asked is, what's the probability of finding the electron in a small volume element d tau? All right, and the answer is modulus of psi of r vector comma t square d tau. This is the probability, and this part we call as the probability density. Okay, I hope you are already familiar with these concepts. Okay, all right, that's what we have got there. So that's the probability interpretation. Okay, now as I said, this psi of r vector comma t, the modulus of square, we can call it as the probability density, because if you multiply it with a volume element, you get the probability. So this can be called the probability per unit volume, or it's a probability density. Okay, and the important thing is that the Schrödinger equation admits a continuity equation of this form. Okay, you might already be familiar with continuity equation, of course, from quantum mechanics and also from electrodynamics, where you have such a continuity equation for charge density. All right, it's associated with conservation of charge. Okay. So in the case of charges, we know that if you have a small volume and if the charges are increasing, this equation says that there should be a current into this particular volume. All right. If the charge density is decreasing in this particular volume, that means that there has to be an outflow. That's essentially what this kind of equation tells us. Okay. So if the probability is increasing within a volume, then we say that there's a divergence, okay, a negative divergence, so to speak. So because you can write dou rho by dou t equal to minus del dot j. Okay. So the probability cannot just disappear, it's conserved, it obeys a continuity equation, and in other words, the Schrodinger equation admits a continuity equation of this form. Okay. You can easily obtain this from the Schrodinger equation. Okay. You can also think of it as a property of the Schrodinger equation. All right. And what is this j vector here? It is minus ih cross by 2m psi star del vector psi minus psi del vector psi star. Okay, you can write this in different forms. We'll be using this particular form to do problems. All right. Now, in competitive examination, it's usual to ask to calculate you to ask you to calculate the probability current density. Okay, probability density and probability current density. So you can, if the wave function is given, you can just plug it in here, and then you'll get the probability current density. Okay, this is a question that can be expected. Okay, for certain wave functions. Okay, so this means essentially that probabilities are conserved. Conservation of probability. This equation you can also call as a conservation of probability, or more correctly, conservation of probability density. Okay, conservation of, or we can call it conservation of probability. Okay, yeah, it's conservation of probability. All right, not density, conservation of probability. All right, now here comes the normalization. All right, so if psi of x square, okay, has some, or dx is a probability, all right, so the total probability has to be equal to 1. Okay, which means that the question you ask is, what's the probability of finding the particle anywhere in space? This has to be 1, because if you are talking about a real particle, it has to be somewhere in space. Okay, so there has to be a non-zero probability of finding the particle somewhere in space. All right, so if you take the whole space and ask the question, what's the probability of finding the particle anywhere in this space? It has to be 1, because it exists somewhere. Okay, all right, I mean, you should always be able to measure it to be existing at some point. All right, so this has to be equal to 1. Okay, within the whole range of positions, minus infinity to infinity. This is for 1 dimension, and here we have it for the 3-dimensional case. Okay, now such functions, okay, the functions that we take for wave functions have to be square integrable. All right, these functions are called square integrable. What do you mean by a square integrable function? So you can say that a function is square integrable in an interval, okay, between a and b, if this quantity psi star psi dx is less than infinity. All right, because only then you can actually normalize only then you can interpret it as a probability. Right, it has to be finite, which means that in the given interval, the psi star psi dx has to be a finite quantity. All right, such functions are called square integrable functions. Okay, so wave functions that we deal with, or wave functions corresponding to physical systems, have to be square integrable in this sense. Okay, it has to be square integrable. Right, so what we are seeing here actually is we have already discussed the scalar product. Okay, we can call psi with phi, it's a scalar product. Okay, you can write this as psi star of x phi of x dx. Okay, within in the whole range. Okay, so now this is the scalar product in the function space. This is how you represent the scalar product in the function space. Okay, this is easy to see. It's not very difficult to see. You can just plug in an identity in here. Okay, and then you will see that identity in terms of the eigenvectors of position operator somewhere in here. Okay, and you can do some manipulations and show that this is equal to this in some representation. All right, so this is how we define a wave function, also the scalar product between two wave functions. Okay, you might be familiar already with this thing. If you have a column vector, okay, let's call it as A, okay, A, B, C, and some B is equal to, what do you call, E, F, G, okay. In this case, the scalar product, okay, these could be state vectors, and in this case, the scalar product between A and B, okay, this is written as A dagger B, A dagger B, which means that it is A star E plus B star F. The scalar product is A star E plus B star F plus C star G, okay. Actually, that's exactly what's happening here also, okay. You can consider this as a continuum version, right? This scalar product here, you can look at it as a continuum version of this A dagger B, which means that if you write all these complex numbers, all right, this psi of x and phi of x are complex numbers, okay. So if you write all these complex numbers in as a column vector, okay, or column matrix, you can of course write this psi of x1, psi of x2, etc. for each position, okay. You will have an infinite dimensional column vector, and then if you use A dagger B, you will exactly come back to this definition. Alright, so these are all related and these are all consistent. So this is what we mean by normalization and the scalar product for wave function. Now, when we do problems or when we actually deal with the physical system, you may actually have to start by normalizing the wave function. Right? Sometimes the wave function may not be normalized. Okay, so then you will have to normalize the wave function. How do you normalize the wave function? You demand that your wave function is what do you say, the wave function, okay, demand that this condition is satisfied. Okay, if this condition is satisfied, we say that it is normalized, and if this condition is not satisfied, for example in this case, we say that integral a to b psi star of x psi of x dx is not equal to 1, but it's some finite quantity a. Okay, some finite quantity a. Now we can normalize the wave function by redefining our wave function as psi of x. Instead of psi of x, you will write psi of x divided by square root of a. Alright. Now, if this wave function is not normalized, then we can normalize the wave function by dividing it by square root of a, where a is given by this relation. Okay, I hope that's clear. This is known as the norm of the wave function. Okay, norm. The scalar product with itself is called the norm of the wave function. All right. Okay. So it's normalization. Okay, so I have written it down clearly here. This is how we normalize the wave function. All right. So if phi is not normalized, which means that we have got phi star of x, phi of x, okay, minus infinity to infinity, dx is equal to some n. Okay, so we need to define a new wave function. We need to define a new wave function psi of x, which is normalized. Okay, so what we do is that we define psi of x as phi of x divided by square root of n. Phi of x divided by square root of n. So obviously, okay, that's correct. So obviously, let's write a here because I have written n. Okay. Why? Because obviously, if phi star of x, phi of x dx integral is a, right? So if you take a square root of a here and a square root of a here, right? Then this will become equal to 1. Okay, that's exactly what we are doing. All right. So generally, let's say that if phi of x comma t is an unnormalized wave function, we can construct a normalized wave function as psi of x comma t is equal to n phi of x comma t, where n is the normalization constant. Okay, so in this case, we can write integral minus psi star of x comma t, psi of x comma t dx is equal to modulus of n square minus infinity to infinity phi star of x comma t, phi of x comma t dx. Okay, this will be equal to 1. This is known as normalization constant. This is the constant that we used to normalize the wave function, and that's equal to 1 by square root of this thing. Okay, 1 by square root of integral phi star phi dx. Right, so if phi star phi dx integral of it all over space is 1, then it's already normalized. If not, we have to divide the wave function. Okay, or divide each of this, or divide the wave function by this normalization factor in order to normalize the wave function. All right. Once we normalize the wave function, we can directly find the probability or the probability density, so to speak, or probability of finding the particle in a given interval. Okay, so that's what we do in quantum mechanics. So let's do a problem here. Let's do a simple problem here. Normalize the wave function given by psi of x equal to n e raised to minus alpha x for x greater than 0 and n e raised to alpha x for x less than 0. Alright, so here a range is given and the wave function is given in this way. Okay, for x less than 0 it's n e raised to alpha x, and for x greater than 0 it's n e raised to minus alpha x. Okay, so this is the normalization condition. It has to be equal to 1. Okay, this means that some normalization constant, multiplied by this thing. Okay, we have got this n here. Okay, we need to determine n. Okay, we need to determine n by normalizing. So we demand that psi star of x, psi of x dx integral, okay, integrated all over space is equal to 1. Right, so from this n we get modulus of n square. Okay, you see that it's a real wave function, so psi star of x equal to psi of x. Okay, this could be complex. All right, this this n could be complex because we are not told what it is, so this n could generally be complex, so that's why we write modulus n square here. Okay, and the range, all right, this whole range minus infinity to infinity, we know that from minus infinity to 0 the wave function is e raised to minus alpha x, so you will have an e raised to minus 2 alpha x there. Okay, oh, that's for x greater than 0. So this is for x less than 0. So minus infinity to 0, that's the range x less than 0. So psi star of x, psi of x would be modulus of n square e raised to 2 alpha x. Okay, this is psi star of x, psi of x, because these are real. All right, this is real, there is no I here. Okay, this is for the range, in the range minus infinity to comma 0, and similarly from 0 to infinity you have got e raised to minus 2 alpha x dx. So you add it because you have to demand that all over the space in which the wave function is defined you should get the total probability equal to 1. So it's minus infinity to 0 e raised to 2 alpha x dx plus 0 to infinity e raised to minus 2 alpha x dx. Okay, that comes from this part. All right, so if you take psi star, psi here, it will be e raised to minus 2 alpha x multiplied by modulus of n square. Okay, you demand that this is equal to 1. Now this is an easy integration. All right, it's an exponential. It's easy. You see that it is, you get so if you integrate this, you get e raised to 2 alpha x divided by 2 alpha and the limit minus infinity to 0. Okay, so you apply the limit, it becomes 1 by 2 alpha. Okay, minus 1 by 2 alpha minus, if you put e raised to minus infinity here, it becomes 0. So you get 1 by 2 alpha from there. Okay. All right. So here, when you integrate, if you integrate this part, it becomes e raised to minus 2 alpha x divided by minus 2 alpha. Okay. So if you apply the limit 0 to infinity, you get this becomes, so for infinity this becomes 0. Okay, 0 minus, for 0 this becomes 1 divided by minus 2 alpha. So it's again 1 by 2 alpha. Okay, because there's a minus and minus here. So you just integrate this, substitute the limit, and you see that modulus of n square this is equal to 1. This means that n has to be equal to square root alpha. Okay, all right, because I'll put one more step here, this is equal to this is 1 by 2 plus 1 by 2 is 1, so 1 by alpha, sorry, modulus of n square 1 by alpha is equal to 1. Okay, this means that modulus of n square is equal to alpha and n is equal to square root alpha. Okay, that's the normalization constant. So if you put this instead of n, the square root of alpha here and square root of alpha here, then our wave functions are normalized. Okay, all right. Here is another problem. Here we are asked to find the probability current density. We need to remember this formula. It's important. Otherwise, you will have to derive it from the Schrödinger equation in the exam hall, which will be a waste of time. Okay, it's not a very difficult thing to remember. Remember that there is this minus h cross by 2m here, then psi star dou psi by dou x minus psi dou psi star by dou x. Okay, for 1 dimension. For 3 dimension, of course, we will have a what do you call the del vector here. Okay, right. So we have given a single wave function, a simple wave function a e raised to ikx. Okay. So solution is minus I h cross by 2m because there's only an x part here. Okay. It's minus I h cross by 2m psi star dou psi by dou x minus psi dou psi star by dou x in the x direction. Okay. So this is basically the x component, the x part, the x component of the earlier relation that we wrote. Okay. We had the relation j vector equal to minus I h cross by 2m psi star del vector psi minus psi del vector psi star. Okay. This is what we had. Okay. Right. Now it's just a matter of substituting it. What's psi star here? It's a e raised to minus I e x. Okay. Of course, this a could be complex, so you have to write a star e raised to minus I k x. Now, if you take dou psi by dou x, it will pull out this I k. That's all. I k a e raised to I k x. Okay. Minus. So we start with psi star of x. What's psi star of x? It is a star e raised to minus I k x. Okay. So you have got a psi here, which is a e raised to I k x, and dou psi star by dou x is minus I k a star e raised to minus I k x. Okay. So if you see that this is, these get multiplied to 1. Okay. And you have got an I k here. This I with minus I is 1. So you have got an h cross k divided by m. Okay. So this is twice. It's exactly the same. It's exactly the same. So what you have in bracket is minus I h cross by 2m. This is modulus of a square I k plus. Okay. Here you have got minus I k multiplied by this minus becomes plus. So I k modulus of a square. Okay. So that's equal to, so this is twice, and this 2 and this 2 cancel, this I and minus I get multiplied to 1. Okay. So modulus of a square h cross k by m is the probability current density. Okay. You can say this is the magnitude of the probability current density. If you want the whole vector, if you want to write it as j vector, then you also need a unit vector here. Okay. In the x direction. It's not very difficult. Okay. You just remember this formula, and this kind of questions have been asked, okay, for different kinds of wave functions. Right. The wave function of a particle moving in free space is psi is equal to e raised to ikx plus 2 e raised to minus ikx. Okay. The probability current density for the real part of the wave function. What's the probability current density for the real part of the wave function? They are asking only the real part of the wave function. But if you look here, all right, if your wave function is actually real, then psi star is equal to psi. Then what does this become? This becomes psi dou psi by dou x minus psi dou psi by dou x for real part. So this is 0. Okay. So if you take only the real part, the probability current density is 0. So 0 is the right answer. Okay. You can actually look at it. If you want, you can take the real part. This is cos kx plus I sin kx. Alright. So the real part from here is cos kx, and from here it is plus 2 cos kx. Okay. So you get 3 cos kx. That's the real part. Now if you substitute it in the equation that we have been using, you see that the probability current density corresponding to the real part of the wave function is actually 0. Okay. Now we have got another part of the question. The energy of the particle is. The energy of the particle is. Right. So how do you find the energy of the particle? So if you remember the postulates, we said that the measured values are actually eigenvalues. Okay. If you measure an energy, it's one of the eigenvalues of the Hamiltonian operator. Okay. So basically we need to find the energy eigenvalue for this. Right. The energy eigenvalue. Right. So this could be an energy eigenstate. Okay. It could be a state with a definite value for energy, which means that if you measure energy a number of times in states prepared like this, okay, you will get always the same energy. Right. Now if you remember, we have got operators. Okay, we have got operators that's equal to minus ih cross dou by dou x. Am I right? Is that the momentum operator? Yes. Yes, that's the momentum operator. Okay. Now since it's moving in free space, right? It's moving in free space. So it has only kinetic energy. The energy, the contribution to energy comes only from kinetic energy. What's the operator corresponding to kinetic energy? Okay, so you can easily do this. You take p square by 2m, the usual kinetic energy for a free particle, and then make it into the corresponding operators. Okay, so it's p cap square divided by 2m. That's the kinetic energy operator. Okay, so this is 1 by 2m, and p cap square is minus I square is minus 1, so it's minus h cross square by 2m, minus h cross square by 2m d by d square by dx square, because there's a square. Okay, it's p square. So this is the Hamiltonian for a free particle, all right, particle moving in free space. All right, now what we do is that we check if this given wave function is an eigenfunction or is an eigenvector of this Hamiltonian operator. What we do for that? We operate this operator, we operate this psi by this Hamiltonian. Okay, you operate this Hamiltonian on the wave function and see if this is equal to some constant multiplied by the same wave function. Okay, if it's some constant multiplied by the same wave function, then this constant is the eigenvalue, is the energy eigenvalue. That's exactly what we are doing. Here we have got the Hamiltonian operator for a free particle, and you act it upon this psi here. Okay, so it's minus h cross square by 2m. First you take one derivative. Okay, if you take one derivative, it's ik e raised to ikx from here, and minus 2ik e raised to minus ikx from here. Okay, you need to take one more derivative, and then another ik will be pulled out here, so that is equal to minus h cross square by 2m. Okay, so ik multiplied by ik is minus k square e raised to ikx. Okay, minus k square e raised to ikx, that's correct. And here you have got minus ik being pulled out here, so minus I multiplied by I is 1, so it's minus 2i minus 2k square e raised to minus ikx. Okay, so this is what we get. Okay, now can we write this as in the form a constant multiplied by the original wave function? That's the question. Can we write this in the form constant multiplied by the original wave function? Okay, sorry, it's, yeah, that's correct. Okay. So that's what we have here. When you take the derivative once more, when you do this derivative, okay, so this thing is after taking one derivative d by dx. Okay, as I said, this ik has been pulled out. If you do one more derivative, you can check this, minus k square e raised to ikx minus 2k square e raised to minus ikx. Okay, now you can pull this k square outside, okay, or actually the minus k square outside, then you see that this is equal to h cross square k square by 2m, h cross square k square by 2m, and what you have, it's e raised to ikx minus or plus, it's plus, okay, because I pulled out minus k square, plus 2 e raised to minus ikx. Okay, see, that's exactly the wave function we started with. Okay, that's exactly the wave function we started with. Okay, so when you acted the Hamiltonian on the wave function, you see that this is equal to some constant multiplied by the same wave function. Okay, this means that the wave function that we started with is an eigenfunction of the Hamiltonian operator. Okay, and the eigenvalue is the measured value of energy. So if you make a measurement of energy on a system defined by a wave function like this, on a particle represented by a wave function like this, then the energy value you will get is h cross square k square by 2m. Right, so the correct answer is option C. We have got h cross square k square by 2m over here. Okay, here is a problem for you. Calculate the probability current density for a Gaussian wave packet. So it's not a pocket, it's a packet. Okay, wave packet. Psi of x equal to a e raised to minus x square by a square plus ip0 x divided by h cross. Okay, so it's not very difficult. You just plug it into the formula and the answer is this. Okay, j vector is given by this thing. Okay, it's obvious because there's this minus 2x square by a square in the in the argument of the exponential, because this is a real part. Okay, it doesn't get cancelled. Okay. But this part, when you take psi star, for example, it becomes minus, and that part will, you will see that it will disappear from the final answer. Okay, so this is the answer. You try this, it's not very difficult, you do it carefully, and then you should get the answer. Okay, this is again defined, the wave function is defined only along the x-axis, so you can just use psi star d psi by dx minus psi d psi star by dx, that thing, okay, with that constant. This is the answer, you please check that. Okay, so with that we'll conclude today's class. In the next class we'll discuss the conditions for a wave function to be a physical wave function. Okay, so there are certain, so all complex functions cannot be wave functions, cannot be physically relevant wave functions or physically accepted wave functions, because the wave function, you will see that it has to satisfy certain conditions if you can call it as a physically acceptable wave function. Okay, we can discuss the conditions in the next session, and also some of the other things related to these wave functions. Okay, so thank you, and I'll see you in the next class.